Many automation and instrumentation systems require monitoring and controlling processes with temperature sensors. A resistance temperature detector, or RTD, is a sensor whose resistance changes as temperature changes. RTDs are accurate and typically maintenance-free. Let's examine how this simple device is used to detect temperature. Many RTDs consist of a length of fine wire wrapped around a ceramic or glass core. The RTD wire is a pure material, typically platinum, nickel, or copper. A typical RTD uses 3 wires for external connections and is designed to be placed in the desired temperature environment. The RTD provides an accurate resistance value which is typically connected to a programmable logic controller. The internal circuitry of the PLC interprets this resistance value and equates it to temperature value. The PLC software uses the RTD value for monitoring and control. An RTD is used as a part of a Wheatstone bridge circuit. A Wheatstone bridge uses 4 resistances in a bridge circuit to provide extremely accurate voltage measurements. These voltages are amplified using an op-amp and converted to digital information using analog to digital converters. Let's examine how the RTD is used in a Wheatstone bridge circuit. Ohm's law is used to calculate the voltage dropped across resistors. In this series circuit, notice that as the resistance of R2 changes, the voltage dropped across each resistor changes. Notice also that when both of the resistor values are equal, the voltage dropped across both resistors are equal. Also notice that as the resistance of R2 increases, the voltage dropped across resistor R2 increases. In this circuit, 4 resistors of equal values are used. Resistors R1 and R2 are in series and connected to a 10-volt source. Resistors R3 and R4 are in series and connected to the same 10-volt source. Notice that the voltage dropped across all 4 resistors is 5 volts. A voltmeter is placed at the center point between the 2 series circuits. Since there is no potential difference at these 2 points, the voltage is 0. This circuit is identified as a Wheatstone bridge. The original intent of a Wheatstone bridge circuit was to find the value of an unknown resistance. However, an RTD can be placed in a Wheatstone bridge circuit to accurately identify a temperature. Let's examine how this works. In a balanced Wheatstone bridge circuit, the center voltage is 0. Notice how the center voltage changes when resistor R4 is replaced with a 150 ohm resistor. The center voltage is now 1 volt. 1 volt is the difference between the voltage drops of R2 and R4. It is also the difference between the voltage drops of R1 and R3. This voltage difference can then be amplified and used as a temperature reference. When an RTD is placed in a bridge circuit, it changes the voltage values of the circuit. An RTD is a very accurate and reliable device that creates linear voltage values from its resistance values. The center voltage of the bridge circuit is typically sent to a high impedance op-amp device. From the op-amp device, the value is sent to an analog to digital converter. The value is then used for temperature control. A resistance thermal device, RTD, changes its resistance with temperature. The standard RTD value creates 100 ohms of resistance at 0 degrees Celsius. As temperature increases or decreases, the resistance of the RTD changes. RTDs produce a linear resistance with temperature changes and, as a result, a linear voltage change in the bridge circuit. There are various types of RTDs. Specifications should be used to design RTD circuits. Let's examine how an RTD is used in a bridge circuit. In this example, the RTD is shown as a 100 ohm variable resistor. When the RTD is close in proximity to the bridge circuit, the resistance of the conductors connecting the RTD can be ignored. However, when the RTD is moved away from the bridge circuit, the resistance of the connecting conductors increase. The increased resistance must be added to the circuit. In this example, the resistance of each conductor connecting the variable resistor is 50 ohms. The combined resistance of both wires is 100 ohms. The resistance of the conductors create problems in the bridge circuit. Let's examine how typical RTD connections correct this problem. A bridge circuit uses 4 resistors. Notice that in order to create a balanced bridge voltage of 0, each set of 2 resistors must be of equal value. In the example shown, resistor values R1 and R2 are equal, and resistor values R3 and Rx are equal. The 2 equal sets of resistor values create a balanced bridge circuit. Let's examine how the added resistance of the conductors used to connect an RTD affect the bridge circuit. First, note that the conductors used to connect the RTD are typically the same size and the same length. Therefore, the conductors have the same resistance. In the example, the resistance of each wire is 10 ohms. Notice the result of the circuit when the RTD is connected. The result is 4 resistor values. The 4 resistance values can be combined to create 2 equal resistance values. In the example shown, the resistance of R3 in one of the connecting conductors is equal to the resistance of the RTD in the other connecting conductor. This creates a balanced bridge. Let's examine how the resistances of the conductors connecting the RTD are used to create a balanced bridge circuit. In this circuit, the RTD resistance is 100 ohms and each of the connecting conductors have 10 ohms of resistance. Resistor R3 is 100 ohms. The 4 resistances make up a series circuit. The resistance of R3 plus the resistance of one of the connecting conductors is equal to the resistance of the RTD plus the resistance of the other connecting conductor. Connecting to the center point of the 4 resistance values creates a balanced bridge. The RTD bridge circuit uses the resistance of the conductors connecting the center measurement device to create a balanced circuit. For a bridge circuit to be complete, a measurement device must be connected in the center of the bridge. Let's examine how the measurement device and the connecting conductor affects the RTD bridge circuit. In the circuit shown, 2 1000 ohm resistors are placed in series and connected to a 10 volt source. Since both resistors are the same value, 5 volts is dropped across each resistor. One of 2 resistors are to be placed in parallel with resistor R2. Which of the 2 affects the voltage of R2 the least? In other words, which one of the resistors, when placed in parallel with R2, results in a voltage closest to 5 volts? When the 10 ohm resistor is placed in the circuit, the voltage of R2 drops to about 90 millivolts. When the 100,000 ohm resistor is placed in the circuit, the voltage of R2 changes only a small amount. High resistance loads have very little effect on a circuit. When a load includes inductive or capacitive reactance, the opposition to current flow is described as impedance rather than resistance. Impedance is abbreviated with the letter Z. When the RTD is connected to a PLC, it completes a bridge circuit in the analog input module. In the analog input module of the PLC, the bridge voltage is used to supply a high impedance operational amplifier, called an op-amp. The high impedance of the op-amp results in no loading effect on the bridge circuit. The op-amp voltage is used by an analog to digital converter in the analog input module to convert the voltage into a corresponding digital value. This digital information is used by the PLC software for programming temperature control and temperature monitoring. The most common RTD has 3 connecting conductors. 2 red conductors and 1 white conductor. Although there are 2-wire and 4-wire RTDs, the 3-wire is the most common. RTDs are typically used in conjunction with a PLC. The PLC must be specifically designed to accept an RTD or have the capability to add an RTD analog input module. RTD connection points are typically found both in the specification information and on the device itself. The module terminals and the RTD conductors are identified on the device for proper installation. In the example shown, the 3 conductors of the RTD are connected to terminals 1, 3, and 4 with an additional jumper from terminal 3 to 2. Resistance temperature detectors, or RTDs, are designed to produce an accurate and linear temperature value. RTD analog input modules on PLCs use electronic devices to convert the voltage values created by the RTD into digital values. The digital values are used by the PLC software for programming temperature control and temperature monitoring. An RTD is an important device for temperature control and temperature monitoring in automation and process systems.